This is a hints video for question 10 of chapters 2 to 5. In both parts A and B, the question essentially gives you a function, here 4 times mu minus mu plus 3, xn plus xn squared, and it asks you to first find the fixed points and then find the regions of stability and instability. Just from this basic analysis, you can actually informally sketch most of the bifurcation diagram. In fact, all of the bifurcation diagram, and this is what this first part of the question is about. It's the second part of the question which ends up being a little bit more algebraically challenging. So I've split it up for you into these 5 steps in order to do the question. Okay, you take the function f of x, and in step 1, you do the usual thing and solve x equal to f of x to find the fixed points. If you do this, then what you should find is that x equal to 4 is a fixed point, and also x equal to mu is a fixed point. Okay. Next, what you want to do is for each of these fixed points, you want to solve for the regions of stability and instability. So for instance, to check for stability, you would check that the derivative lies between -1 and 1. When you do this, you should come to the conclusion that x and mu, in the cases in which x and mu is 4 and 4, this is a transcritical bifurcation. In the case where x and mu is 4 to 6, this is a period doubling bifurcation. And in the case where x and mu is mu and 2, this is a period doubling bifurcation. Okay. The first 2 bifurcations correspond to the first fixed point of x equal to 4, and then the second one, the mu2 bifurcation, corresponds to the x equal to mu fixed point. Just using this information, you're able to construct, in fact, most of the bifurcation diagram, essentially all of the bifurcation diagram. So I'll do this together with you. You make your mu axis, you make your x axis. You know, firstly, that x equal to 4 is a fixed point. Okay, so we'll just do this dotted for now. Next, you know that there are critical points at 2, 4, and 6 along the mu axis. And you know that the other fixed point is given by x equal to mu. So in this bifurcation picture, again, just dotted for now until we plot the stability and instability, it must look like so. You know that this 4, 4 point is a transcritical bifurcation. You also know that there's a period doubling bifurcation at mu is equal to 2 and mu is equal to 2 and x equal to mu, and there's a period doubling bifurcation at mu is equal to 6 and x equal to 4 over here. Okay, so there's one period doubling here, one period doubling here, and on your own, what you want to do is you want to fill in this dotted line, either dashed or solid, for stability or instability. Okay, so that concludes these first 3 steps. That's essentially the easy part. The next 2 steps correspond to doing a local analysis for the Taylor series. Essentially what you want to do is you want to develop the Taylor series around each of these bifurcation points and then compare the Taylor series coefficients to what we derived in the lectures and what you can find in the typeset notes. Okay. The first step is to essentially shift the coordinates so that you have a Taylor series at 0, 0. This is just more convenient. So for example, what you would do for the 4, 4 point is you would let y be equal to x minus 4 and then lambda equal to mu minus 4. And so y and lambda are the new coordinates so that both of them are equal to 0 at the critical point, at the bifurcation point. Similarly, for the point 4, 6, x and mu equal to 4, 6, you want to let y be equal to x minus 4, and then let lambda equal to mu minus 6. So again, now y and lambda are equal to 0, 0 at the bifurcation point. And then finally, for the point 2, 2, where x is equal to mu along this curve, you want to let y be equal to, I'll do this one second, you want to let lambda equal to mu minus 2. So now when mu is equal to 2, lambda is equal to 0. And you also want to let y be equal to x minus mu. And the below gives you that this is x minus lambda plus 2. Having done so, what you're going to do is you're going to substitute these relationships into the function and then reorder terms so that you have a Taylor series expansion. I'll do this first, just as an example, I'll do this first for the 4, 4 point. Okay, so you let y be equal to x minus 4 and let lambda equal to mu minus 4. Okay, and we usually have the relationship xn plus 1 is equal to f of xn. So now we have a yn plus 1 plus 4 on the left-hand side equal to 4 times, instead of mu, we have a lambda plus 4, minus, instead of a mu plus 3, we have a lambda plus 7. Instead of an xn, we have a yn plus 4. And then this is a yn plus 4. What you do is you reorder this as a yn plus 1, and you should have an h of y here, an h of y function, which you should move the 4 to a minus 4 to the right-hand side. And when you do this, and you simplify everything down, you can verify that you should have yn minus lambda yn plus yn squared on the right-hand side. Okay, so the key idea is now you want to solve y equal to h of y when y and lambda are small. Okay, in fact, I can help you do this. I have y is then y minus lambda y plus y squared. And then you see that you have now y squared is essentially lambda times y, and y is equal to lambda if y is not equal to 0. Okay? This is a transcritical bifurcation. Think about why that's the case. So this concludes the analysis for the 4 point. By the way, now instead, if you didn't want to do this, if you didn't want to go ahead and solve directly for the fixed point itself, what you could have done is you could have returned to here, and you can check the Taylor series coefficients. This is, in fact, if you look at the solutions, this is what the solutions do. So the solutions will say that A0 is equal to 1, it'll say A1 is equal to 0, B0 is equal to 1, B1 is equal to -1, and so forth, based on the form of this right-hand side. Then you can go to your lecture notes or your typeset notes and verify that these were indeed the Taylor series coefficients that we had derived as corresponding to a transcritical point. Finally, this is now step 6. Finally, in step 6, we have to do a slightly more painful local analysis near the two period doubling bifurcations. If you remember from the analysis we did in the lectures, this ended up being a painful derivation because you essentially have to look at the double iterated map. You have to look at h of y. So you see, if we shift the map as before, we would need to solve y is equal to h of y in order to find the period doubling bifurcations. And instead, I'm not going to require for you to do this. Instead, I'm going to give you the h of y map here in these two lines. Okay, so near the suspected period doubling points, 2, 2, and 4, 6, those are the h of y maps. And so essentially all you have to do is solve y is equal to h of y. So essentially replace yn plus 2 here and yn with y. So let's do that for this top line so you can see what it's all about. Okay, so suppose we want to solve for the period doubling bifurcation near 2, 2. Okay, then you just want to solve y is equal to 1 minus 2 lambda y minus lambda y squared minus 2y cubed plus lambda squared y plus dot 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 in the limit that y and lambda are small. You're always looking at where y and lambda are small. Okay, so first that you see that this y on the left hand side will cancel with the 1 times y on the right hand side. So this essentially gives you 0 is equal to minus 2 lambda y minus lambda y squared minus 2y cubed plus lambda squared y plus dot dot dot. Okay, so when you do the dominant balance, if I call this one 1, 2, and 3, you can argue that 2 will always be smaller than 1 because this is a y squared and this is a y, lambda y squared and lambda y. And so you would have to involve 3. So the dominant balance turns out to be 1 and 3. And if you cancel the y, if you assume that y is not equal to 0, that's fine. You then have 2y squared is like minus 2 lambda. And so this tells you that y squared is like minus lambda, or y is equal to plus or minus root of minus lambda. Okay, and you can verify, this is approximately equal to plus or minus root lambda, you can verify that this is a consistent balance under this assumption that you were right to neglect 2, 4, 5, 6, etc., etc. Okay, these give you the two arms of the bifurcation for the period doubling point. Okay, if you didn't want to do this, and if you look at the solutions don't do it in this kind of what I think is an intuitive way. They do it by comparing it with the Taylor series coefficients. So again, what you can do is you can compare with the Taylor series coefficients here. So you can go and find out the A0, A1, B0, B1, B2, etc. values for this expression on the right-hand side, and you can then compare with the typeset notes. Once you've done this, so once you've done the 2, 2 analysis, you'll do the same analysis for the 4, 6 point. This ends up being very, very similar. It's as quick as we've done it here. So in a sense, I've already done the analysis for you. It's up to you to do it yourself, write it out, and really understand it at a much deeper level.